Hello, welcome to School's Not Out, your daily classroom for CSEC and CAPE students. Today's lesson is on CSEC chemistry. I am Roger Dawkins. All right, so yesterday we started on the topic of organic chemistry. All right, now we should already understand what this joke here is saying. All right, help save me, I'm dying, and this organic molecule is saying I'm trying to save you. All right, now if we remember that die means two and in means that there is a double bond present, right? So one double bond, two double bonds, so that's why it is saying I'm dying, right? And this one is saying I'm trying because there's three double bonds. All right, so let's recap what we did yesterday. All right, so organic chemistry is the chemistry of carbon compounds, right? And those that contain only single bonds, they belong to the group alkanes. And those with double bonds, they belong to the group alkenes. And those with the hydroxyl group, that OH group that we are so familiar with right here, they are called alcohols. All right, now structural isomers, as we continue our recap, are molecules that are the same, type of molecules, same number of atoms, but the way that they are arranged is very different. All right, now when naming, right, remember that chemical nomenclature, right? When naming the carbon atom closest to the functional group, that is where you must start counting. All right, so if I have C double bond C, right, and already we should be shouting out the answer that this is propene because 3. So H. We would not start counting here because the functional group is right here. So remember, you must always start counting at the carbon atom closest to the functional group. So it would not be 1, 2, 3, but instead it would actually be this direction. 1, 2, 3. All right, so then this would be 1 propene. All right, so you must start counting from the carbon that's closest to the functional group. All right, so learn that, study that, date it. All right, make sure you know it. All right, so let's move on. Now, I have a question here that I want you guys to try while we go through this lesson. So you were to name this compound. All right, so we see here, this is the straight chain, and here we have our side branches. All right, now all we have done is condensed the formula. So let me show you something. So again, if I had C to C double bond C, right, and we should know by now that all the lines that are sticking off represent hydrogen. All right, so all I've done in the example here on the slide is condense it. So you have one C here, and how much H's are attached to it? 3. 1, 2, 3. So it's CH3. How much bonds are between this carbon and this carbon? It's 1. All right, so you'd put C again. There's only one H. Here we have a double bond, so we're going to put double bond, and then C again, and then 1, 2, 3. All right, so this is how we can condense this into this. So that's all I've done with the example on the slide. So all you're going to do now is name the compound on the slide. All right, so you can work out that while we continue throughout the lesson. All right, so alkanes now. So they form isomers through branching. The other homologous series, they can form isomers through branching as well as moving the functional group. All right, so if we take a look here at an example of butane, which is a alkane, right? On the left side we see N-butane. N simply means normal, which means it's just a straight chain. It's an unbranched chain. Very obvious here, there's nothing coming off the sides, right? So N means normal. So we have normal butane, and on the right we have 2-methyl propane. Now if you realize, both of these have the same molecular formula because it has 1, 2, 3, 4 carbon, right? And then 1, 2, 3, 4 carbon, right? And it would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen, same 10 on this side. So they have the same molecular formula. But the only way alkanes can form isomers is by branching, all right? All right, now let us look at the board. For something like butene, which is 4, 1, 2, 3, 4, right? We drop on our hydrogens as usual. Now for something like butene, right? As we say, only the alkenes can form isomers through branching, but the other homologous series, they can utilize branching as well as moving the functional group. So if all we do here is move the functional group of the double bond to carbon 2, so end up with something that looks like this. This is an isomer because we have moved the functional group. All right? We can also form an isomer, so we can put back it on carbon 1. So let me erase this off the board. So let's go again. 1, 2, 3. And if we put a side branch there, right, this is also an isomer. But if you realize this time, I did not move the functional group from carbon 1. See there? So carbon 1, it's still on carbon 1. What I've done instead is move one of the carbons to carbon 2. So now you have a branch. All right? So again, alkanes form isomers through branching. Alkenes form isomers through branching as well as moving the functional group. All right? All right, so now, we can look at the same thing for alcohols, all right? Remember, alcohols, they're the ones that have the OH group or the hydroxyl group, all right? So if I have 1, 2, 3 OH, immediately it should jump out at us that this is going to be an alcohol because there's the OH group there. So H, 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 all right, 1, 2. All right, so one thing we need to be careful because sometimes I realize that students don't pay attention to these things. Carbon must always have 4 lines coming off of it at all times, must have 4. All right, so now, remember we start counting the closest to that's right, the functional group. So we're going to start counting here. So this is carbon 1, this is carbon 2, and this is carbon 3. All right? So 1, 2, 3. So as a result, the name of this compound will be 1-propanol because it's on carbon 1. All right? Now, if I were to move the functional group to carbon 2, so now we have C to C to C. So now move the hydroxyl group to carbon 2. All right. So now this time it will be 2-propanol. All right. So we have moved it to propanol. All right. So here on the diagram, right, we see we have butan 1-ol, or we can say 1-butanol, butan 2-ol, 2-methylpropanol, or 2-methylpropan 1-ol, and 2-methylpropan 2-ol. All right. So again, don't let the names fool you. All you need to look at is the parent chain, and then look at the side chain. All right. So here, when we say propan 1-ol, the 1 is telling me that the OH group needs to be attached to carbon 1, which is what we see here. All right, so propan 1-ol, so the parent chain is that. And in the 2 tells us which carbon the side branch is attached to, which is carbon 2. All right? All right. So sources of hydrocarbons. So these are naturally occurring inside the earth, and the liquid form is known as crude oil or petroleum, right? The gaseous form will be known as natural gas, but the liquid form is known as crude oil or petroleum. And this has to be separated into its various components for it to be of any use to us, because the smaller the amount of carbon, the lighter or the more gaseous the compound. All right, so for instance, like methane has 1 carbon, it's a gas, but like decane, which has 10 carbon, it tends to be a really heavy liquid or a solid, right? So can you imagine now if you had your gas stove which contains methane and it had a mixture of decane and octane and hexane, these heavier carbon compounds. So you go your stove and you try and turn it on and you try to light it, not happening. Why? Because the decane and hexanes are too heavy. They can't flow up into the stove. All right? So for petroleum to be of any use to us, we have to separate them into its components. How do we do that? Right? We do that through what we call fractionating distillation. All right? So look at the screen. So this is a fractionating column. What we do, when we collect our natural source of petroleum or the crude oil, we insert it at the bottom of the fractionating column. All right? So it goes in at the bottom at around 350 degrees Celsius, very hot. All right? Now, the lighter hydrocarbons, they have a very lower, what we call boiling point, right? So they become a gas very easily. So at 350, they become a gas super easy. They go up straight to the top of the column, right? But those that have more carbons, right, they tend to have a higher boiling point. So as a result, like decane and hexane and octane, they will stay down here so. All right? So if you look to the right of the diagram, where it says C50 to C70, those heavy, solid kind of hydrocarbons tend to collect at the bottom, right? And as you go up, you realize that the number of carbons are decreasing, which means the compound or the hydrocarbons are getting lighter and lighter and lighter, or smaller, if you will. Now, at the bottom here, what we call bitumen, that's where all the hydrocarbons that are above 70, they will be collected down here. Now, this is what we use to tar our roads, right? So when you're driving and you're dropping about 4 potholes while on the way to school, right? It is bitumen they use to kind of seal off the road so that it becomes very smooth, and some people take it like Dover, right? All right. Now, thermal cracking. When alkanes are large, right, like our octanes, right, and our decane, right, they're very large, we can heat them at high temperatures and pressurize them. And doing so will break them up into smaller alkanes. All right? Now, thermal cracking always produces at least 1 alkene. So if you get a question on thermal cracking, you must produce at least 1 alkene or your answer is incorrect. All right? So thermal cracking always produces at least 1 alkene. So here's an example. All right? So we have 1, 2, 3, 4, 5, 6, 7. Right? So it's hept, and they're all single bonds, so it's an alkane, so it's heptane. So if we apply a lot of heat, a lot of pressure to heptane, it will end up breaking. And so we get 1 alkene, remember the double bond, and we have 1 alkane. Now the amount of carbon and the amount of hydrogen from the products must be equal to what the original compound had. All right? So 1, 2, 3, 4, 5, 6, 7. So 7 carbons are there. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. All right, same thing up here. So all you're doing, you're breaking this large, unnecessary alkane down into more useful alkanes plus an alkene. All right, so please remember, always produces at least 1 alkene. You can produce more, but at least 1. Very good. All right. So alkenes, due to their saturated bonds, remember saturated means that they have single bonds. So due to their saturated bonds, they are generally unreactive, right? They're not really doing much because they're kind of satisfied, right? Imagine, you're married, you have your 2 kids, you know, you have a nice job, right? So you're satisfied. People don't really bother you, especially like old people at them old age. Things don't bother them too much. They live life and yeah, so they're kind of unreactive, all right? So alkanes now, they undergo mainly 2 types of reactions, all right? Combustion and substitution reactions. Combustion, as we should probably understand, means to burn, all right? Burn, burn. All right, so when oxygen is plentiful, alkanes will undergo complete combustion. That means they will finish off, all right? And they will form carbon dioxide and water in the form of steam, right? A gas. All right, so that is when oxygen enough, when it's nice, all right? When oxygen supply is limited, right, alkanes undergo what we call incomplete combustion, right, to form carbon monoxide. All right, so look at the difference. Complete combustion gives you carbon dioxide, and incomplete gives you carbon monoxide. All right, so please pay attention to that. So once you're complete, you complete me, carbon dioxide. Incomplete, carbon monoxide. All right, now alkanes burn with a clean blue flame. You can see that from your stove. Turn on your stove, nice blue fire. All right, so here is a balance equation for complete combustion of methane. So again, so the alkane plus oxygen gives you carbon dioxide and water, right? And in incomplete, methane plus oxygen gives you carbon monoxide plus carbon dioxide and water, all right? This is a visual look at what the molecules are about. So here we see the methane, 2 oxygen, and all this, that's happening that they're being rearranged to form the carbon dioxide and the water, all right? So substitution reactions. So under UV light, sometimes you can use sunlight, but UV light is the best light. So under UV light, alkanes can react with halogens. If we remember, basic 9th grade chemistry, halogens are in group 7, right? Your fluorine, your chlorine, your bromine, your iodine, or iodine, that's what people call it, right? Those are your halogens, group 7. Now, the reaction with halogens can also be called halogenation. The halogen will replace the hydrogen atoms in the alkane 1 hydrogen at a time. The stronger the UV light, the faster the reaction, right? So all that means is the more intense the UV light, the faster the reaction. Now, whenever we use halogens, these are our side chain prefix, all right? So if the halogen is fluorine, it will convert it to fluoro, chlorine, chloro, bromine, bromo. Yeah, bro. All right. So here is a reaction of methane and the halogen chlorine. All right. Now it takes place in steps. Now remember what we said. It replaces hydrogen 1 at a time. So it now replaces all hydrogen at once. All right. So 1 hydrogen is replaced with chlorine. So you get CH3, CH3Cl. Then that one is replaced again. You get CH2Cl2. Then you replace again CH2Cl2 to get CHCl3, and then the last one is the CHCl3 is replaced to form CCl4. All right, so it takes place in steps. All right, so the first hydrogen comes off, then the second one, then the third, then the fourth. All right, so the overall reaction would be this: CH4 plus 4 chlorine will give you CCl4 plus 4 molecules of hydrogen chloride gas. All right. The products of halogenation are called haloalkanes, or they're called alkyl halides. Now remember, alkyl simply means side branch. Halides mean they come from the halogens. All right. So it's a side halogen. The more reactive the halogen, the faster the reaction. All right. So we know that fluorine is the most reactive halogen. So any alkane reaction with fluorine will be very fast, right? Chlorine will be kind of an in-between, and then bromine will kind of be slow. Iodine don't react with any alkane at all, all right? It's too unreactive compared to the others, so it doesn't produce a reaction, all right? All right. So we're looking at alkene reactions. All right. So the presence of the double bond makes alkenes more reactive than alkanes. All right. So if alkanes, right, were like the old people who live them life to the fullest and nothing really bother them again, alkene would be like the young people who want to prove themselves, them have what things they want to deal with, right? So they're kind of reactive. So they undergo a lot of reactions. Alright? So alkenes also produce carbon dioxide and water during combustion, but this time it produces a smoky flame. Alright, so alkanes, the one with A, when they are burnt, it produces a nice blue flame. While alkenes, when those burn, you tend to see a little black smoke coming off of it. So if you think about like your candles, when you light them, sometimes you look at it, you see, look, it's some black wisp coming off of it, alright? Because alkenes are inside of those. Alright. Now, alkenes also undergo halogenation, but in their case, halogens are added to the structure instead of replacing a hydrogen. Alright? And in this case, no UV or sunlight is necessary. It can take place in the dark. Again, alkanes don't tend to be reactive, so they need a push. Alkenes, they want to prove themselves. I'm a big man, I'm 18 now, I can do my thing, right? So they have a lot to prove. So they don't need any boost. They can just react with halogens, all right? So here we have an example of ethene reacting with bromine gas, all right? So here we see that the double bond opens up. All right, the double bond opens up to accept the bromine gas. All right, so let's look at the board and see what we have going on. So here we have our ethene. Right, so what happens is that the structure opens up. So we're going to end up with CH. All right, so this opens up. So you still have your 4 hydrogen. Let me separate this. You still have your 4 hydrogen. So 1, 2, 3, 4. All right, 1, 2, 3, 4. So all the structure does is open up. So now when you add your bromine, right? Remember, halogens are diatomic. They don't exist by themselves. All right, so when you add your bromine, 1 bromine goes here, and the other bromine comes here. All right? So it's an addition reaction because you're adding something to the alkene structure. All right? So again, if you react an alkene with a halogen, you get a haloalkene, right? Because halogens are still a part of it. All right? So 1 bromine goes here, 1 bromine goes here. So you're adding. So in alkanes, you substitute. In alkenes, you are adding. All right? Beautiful. All right. So alkene halogenation also results in the formation of haloalkanes. So remember, halo means that you have added a halogen, and alkane means that it only contains single bonds. That is correct. So if we take a look on the board, right, we will see that the bond between the carbon has changed from a double bond to a single bond, which means that this compound is now an alkane. All right, it is now an alkane. And because halogens are now in it, it's called a haloalkane. So alkane halogenation and alkene halogenation, also, they both produce haloalkanes. All right. Now, uses of alkenes. They can be used as fuels because they burn very easily and they release a large amount of energy during combustion. All right. And because they are non-polar, they can be used as solvents as well. All right, so like petroleum jelly is just oil that is dissolved in paraffin wax. All right, so it's used, so alkanes are used as fuels and they're used as solvents. All right, so we're going to move on to some possible questions. All right, so let's look at the first one. So it says ethane burns with a blue flame in oxygen to produce carbon dioxide and water. And you were to write a balanced equation for the reaction. So we're going to take our time and go through this, all right, as much practice as possible. So ethane. So if you remember the formula, right, it is, so ethane will be CnH2n plus 2. Remember, that's the formula for alkanes. So it would be C2, 2 times 2 is 4, plus 2 is 6, all right? So ethane plus oxygen will give you carbon dioxide and water. Now we need to remember our state symbols. A lot of times we leave off our state symbols. All right, so it's a gas, 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 and gas. All right, and we're applying some heat. All right, so we need to balance this equation. All right, now my advice to students is to always start immediately after the arrow. All right, now I can do this quickly out of my head, but one way I recommend students to practice this, if they're not really so good at balancing, write out everything on the left side and everything on the right side in terms of the elements. So which element is here on this side? We have carbon. Let me use a different color. So we have carbon, we have hydrogen, and we also have oxygen. All right? And remember, in a chemical equation, any element on the left must be on the right. So we also have carbon, we also have hydrogen, and we also have oxygen. All right? So how much carbon is on this side? 2, so you see 2. How much hydrogen is on this side? 6. And how much oxygen is on this side? 2. Let's go to this side. So 1 carbon, 2 hydrogen, and 2 and 1 is 3. So we have 3 oxygen. All right. So we start after the arrow. So carbon, 1 on this side, 2 on this side. How do we change 1 to 2? All right, and we use multiplication. How? That's right, we multiply this by 2. All right, so we're going to put a 2 in front of the carbon dioxide. So now we have 2 carbons on this side. However, remember, in carbon dioxide, there is oxygen. So if you have 2 carbon dioxide, that means you now have 4 oxygen in all. All right, sometimes students have a hard time visualizing this. So let me show you down here on the corner. So we have carbon dioxide. So this is C, and they say that's O, and that's O. So that's carbon dioxide. If you have 2 carbon dioxide, that means there's a next molecule of carbon dioxide present. So that is why we say you have 2 carbons, right? But now you have 1, 2, 3, 4 oxygen, all right? So oxygen changes to 4 plus the 1 out here, so it would be 5. All right. All right. So now we'll leave oxygen for last, always. All right. Hydrogen. So we have 2 on this side, we have 6 on this side. How would you change 2 to 6? You multiply it by 3. All right. Put a 3 here. So now this changes to 6. Again, you are affecting the oxygen. So there's 4 and there's 3. So that is what? 7. So 4 and 3 is 7. All right. So now, 7 oxygen, 2 oxygen. How do you change 2 to 7? You multiply by 3.5. All right. So 3.5. And all you do, you times everything by 2. So you get 2, 7, 4, and 6. All right. So let's move on to our next one. So it says ethene undergoes a halogenation reaction to form 1,2-dichloroethane. So we are to draw the fully displayed structure. So I must show everything that make it up. So let's answer that question right now. All right. So fully displayed structure of ethene. So remember, ethene. Ene means that there's a double bond there. So And the E means there's 2 carbons. So 1, 2, and the E means double bond. So you're filling everything else with the H. Simple as that. 2 marks, all right, on the way to pass in CSEC, all right? Then it says to draw the fully displayed structure of the 1,2-dichloroethane. So the question said that ethane underwent halogenation, all right? So halogenation means you're going to add chlorine to it. So we have our chlorine here. All right. So whenever alkenes undergo halogenation, it's an addition reaction. And so what it means, you're going to open up the structure. All right. So C to C. So remember, always have 4 lines coming off of your carbon. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. And it says 1,2-dichloroethane. So 1,2-dichloroethane. Remember, ethane is a pairing chain, so we see that right here. Chloro means that it contains chlorine, and di means that there's 2 chlorine. So dichloro, 2 chlorine. And the 1, 2 tells us what? That's correct. The position of the chlorine. So carbon 1, we're going to have a chlorine. And carbon 2 will also have a chlorine. All right? So this would be 1,2-dichloroethane. All right? So again, you pass this part of your CSEC exam. All right? Beautiful. So here on the screen, we have 2 fully displayed structures of 2 hydrocarbons, A and B, that are shown. All right. Now, the next questions will say, what homologous series do they belong to? All right. Now, if we look at compound A, we see a double bond. So easily, we know that it's a alkene. Very good. And on B, we realize that there are only single bonds, right? There's no double bonds, only single bonds. So therefore, B would belong to the alkane group. Very good. All right. So the next thing we're going to move on to is the general formula for B. All right. The general formula for B. And B would be the alkenes. All right. So if we remember from lesson 1, the general formula for alkenes would be CnH2n. Easy. Easy, 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 1 mark. All right. Then it says on the slide that both A and B, right? So we're looking at the third part of the question. So it says both A and B react with chlorine, but under different conditions. All right. So state 1 necessary condition for B to react with chlorine. Now, if we recall, B is our alkane. All right. So what is 1 condition alkanes have to have before they can react with halogens? Right. They must be in the presence of UV light or sometimes sunlight, you know, if you don't have access to UV light. So they need UV light or sunlight to carry out halogenation. So that is the condition for compound B, UV light. All right, let's look at B now. It says to draw the fully displayed structure of the organic products for the reaction of A and B with chlorine. All right. So let's move up. So that was A, which is propene. So C, double bond C. All right. So this is A, which is propene, or 1-propene, if we want to be very specific. And then B would be butane. So 1, 2, 3, 4. All right, we're dropping in our hydrogens. And what do we call this butane as well? We can also call it N-butane, that's correct. All right. So N-butane. Now it says that they both undergo halogenation. So we're gonna add our halogens, right? Chlorine. And then this will end up giving us a haloalkane. So C to C to C. Everybody opens up now. All right. And this also gives us a haloalkane. So in this case, the Cl, then H. All right. And for this one, we also get something similar. So there we go. All right. So there we go. So when one propene undergoes halogenation, you get a haloalkane, and it's an addition reaction. But when N-butane does it, you get a substitution reaction because two of the hydrogen are replaced with chlorine. All right. All right. So it says that we must draw the fully displaced structure of one structural isomer for each of compounds A and compounds B. So we need one structural isomer. All right. So let's get back to the board. So we're going to use the same compounds from before. So let's rub off these. All right. Any questions that you have, just send them to the aforementioned platforms. All right. So it says structural isomers. So let's look. Isomers again. Remember that they are just being arranged differently, or the position of the functional group is changing. So for this, right, propene, so C, double bond C. Now, if you realize, right, that this would not be an isomer because all I've done really just turn it around and bend it. All right, so you can't form an isomer from one propene like that, and you can't branch it either. All right, but this one you can do it. So you have C, and you move this one, come here, so. All right, so 1, 1, 1, 1, 1, 1, 1, 1, 1. So H, 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 and H. All right. So this one, all you have done is taken with the carbons and attach it to carbon 2. All right. All right. Now, if we look at the screen, we see two compounds again. It says which homologous series do they belong to. Again, only single bond between the carbons. That means an alkane. This one is an alkene. State the name of it. Let's look at compound A. All right. So the straight chain or the continuous chain would be 1, 2, 3, 4. Right, that flat line right there. So it is going to be butane as a parent chain. And carbon 2 is where you see that side branch coming out. You see there? So 1, 2, 3, 4, and so 2 here is where the side branch is coming off. So the parent chain is butane and the side branch is on 2. So this will be 2-methyl butane. All right? 2-methyl butane. Let's look at compound B. All right? So 1, 2, 3, 4. So carbon 2 is where the double bond is. So this would be 2-butene. All right? Beautiful. So It says that we're going to get isomers now from compound A and isomers from compound B. So compound A, right, is 1, 2, 3, 4, right? And you have a C group coming off of it. All right, so all we can do for this is just move this come to the side. So you can end up with pentene. So 1, 2, 3, 4, 5. All right, so this is an isomer of that. All right, so for compound B, you're going to work that on your own. All right, so you can ensure that you understand what it is that you're doing. And I hope that we have enjoyed our lesson for today. And that's all for CSEC chemistry. All right, we hope you grasped some of the points we discussed.